spent quite some years together with Elke at University of Saarland, so we know each other quite well. Elke did her PhD, she graduated Uni of Kaiserslautern, and then she joined University of Saarland to do her PhD with Christoph Becher. During that time, she also was part of the excellence program for female researchers. Then she moved as a postdoc to University of Basel, where she also acquired several stipendiums from Robert Bosch Stiftung and Daimler-Benz Stiftung. And then she started her junior group at University of Saarland, which she was leading for 5 years at University of Saarland. And then she moved with the group to University of Kaiserslautern, first as junior professor. And now, since 2 years, she is now a full professor. And she will tell us today about her work with color centers and diamonds. So you are allowed, it's fine with Elke, if you shoot your questions during her talk, don't wait till the end, it's all fine. And general announcement, we will send this list over the rows. Please fill it in, it's important for the coffee break catering. Good, thank you, go ahead.
You tell me if this works with the microphone? Thumbs up. Okay. Thank you very much. Thank you very much, Adashta, for the introduction, and welcome to this talk. For those of you who maybe know me and think I have changed university, it's not that I have changed university again. Since the 1st of January 2023, we are now the Rheinland-Pfälzische Technische Universität Kaiserslautern-Landau. It was Technical University of Kaiserslautern before. It's still the same university. You probably also read here, I am officially a professor of biophysics. Don't be scared, I'm not going to talk about biology today. So I'd like to give you a bit of a general introduction, general summary, what we do with color centers and diamond, and what novel approaches we go here for sensing, what technology is behind all this. And first of all, I have a bit of a general motivation slide, right? For people working in quantum technology, often it splits up a bit into the people doing sensing and the people working on the other pillars of quantum technologies. And for us, when we think about sensing, we are not so much talking about the fundamental quantum mechanics or quantum control and quantum information, but for us, it's rather we want to use the quantum systems as sensors. And even if we don't use any quantum effect, this can already be useful because typically the quantum systems, in this case, our color centers, they are atomically small, and it's good to have an atomically small sensor. But of course, you can also enhance this using quantum effects for metrology. You just saw a talk about, well, I'm not sure if you have to call the T1 already a quantum effect, but maybe yes, yeah. It's not an entanglement, but it's already about lifetime. You can also use coherence in the system to do measurements that you cannot do with a classical system. And in all this, you want to go for an enhanced sensitivity. And you will see what is often easier to do is enhanced spatial resolution because you're using that tiny sensors. And this will be, you will see this at some points in my talk. And as I said, our quantum system of choice are the color centers and diamond, especially the NV centers and diamond, but it's not limited to those. And it's also not limited to diamond. We also have work where we work, for example, with color centers in silicon carbide. Yeah? But for this talk, I'm going to stay with the work on the diamond. So why are the color centers and diamond especially interesting as sensors? You probably all know that diamond is a highly transparent material. It's actually one of the most transparent materials you can get from really the ultraviolet, 200 something nanometer to infrared. We'll come back to that in a minute, why this is interesting. And if you ask my colleague from life science, the first thing they think about for the diamond is that it's carbon, so it's biocompatible. This is if you think about putting diamond particles in cells or so, this is important. But you also have, of course, a very hard, a very inert material, and because the C12 isotope doesn't have a spin, it's almost spin-free. This is also one reason why silicon, the diamond is especially interesting. The color centers for us, they are artificial atoms. They are stable, even at room temperature. They have the long-lived, highly controllable spin states that make them very interesting as magnetic sensors. And that's not the only thing. I'll come to that also on the next slide. The magnetic sensing is just the most prominent one, sorry, but it's not the only thing you can sense for the color centers. They also couple, for example, to crystal strain. So your color center is also a sensor for the strain in the crystal, and they also react to temperature. I'll show you an example of this also on one of the next slides. So, what can you sense with these color centers? As I indicated, you can sense magnetic fields. I draw here the classical North Pole, South Pole magnets, right, to indicate an ordered magnetic system. But as you have already heard in the talk before, you can also sense the fluctuations. And this, I use this unoriented spins here as a symbol. But you can also sense temperatures. And here I use another symbol. This is the radiation pattern of a dipole. So I will show you during the talk. People always think of the color centers as a spin, but we should also keep in mind that they are, as an emitter of light, they are an electric dipole. And this also gives you new opportunities for sensing. And I will show you that during the talk. Now, I've advertised a lot that these color centers, they are atomically small, right? But that does not necessarily mean that you end up with an atomic resolution in sensing. Because if you just have a color center and you image it, or you have to shoot a laser on it, right? We heard this to excite the fluorescence. So when you just do this, you're still limited by your optical resolution, by diffraction, by the Abbe limit. If you want to overcome this, you have to crank up a bit your complexity and technology. And this means you have to have your color center in a scanning probe, and you have to scan the sample under investigation. Think of it like of an AFM. Yeah? You're following the topography, and while your tip with the NV center is following this topography, you are measuring the different quantities you want to look at. As I said, technically this is quite complex. The advantage of this technique is your spatial resolution is given by the distance of your color center to the sample under investigation. So you can go far beyond the diffraction limit. And what I'm going to discuss in this talk at some point, you cannot just sense one quantity, you can sense several quantities. The color centers can be multifunctional sensors. This is the idea behind the approach we take to sensing with color centers. And I will show you a lot of the technology that is behind realizing such an approach. Okay, here also, as we already had the introduction here, I'll keep it a bit short. Yeah, you have your ground state of the NV center. You have one of the spin states, which due to internal dynamics leads to brighter fluorescence than the other two. And you can address these transitions with microwaves, which leads to this, well, the experiment at the heart of all the magnetic sensing, which you call the optically detected magnetic resonance that you can see here. Huh? If you're increasing the B field, the splitting between the 0 to plus and the 0 to -1 transition splits increases, you get a higher splitting. What we did not discuss in the talk before is what determines the sensitivity to your magnetic field. You see here the sensitivity eta. What's in there is several factors. Okay, forget about the constants, right? We can, of course, not do anything to that. But that second term you see here, you see in the delta nu, this is the width of your ODMR line. And this is the point where the diamond material comes into play. Because the more strain, the more charge hopping and so on, the wider your lines get. So this is the point why we are also all the time working on the material. Then you have to see, this is the contrast between your dark and your bright state. This is something we cannot really influence. There are some new techniques how to better read out the spin. So you can work on this, but mainly this comes from the NV Center. And the second thing we can work on is this I0 you see here. This is the photon rate, the count rate you get from a single NV center. And because of this, you will also hear me talk a lot about photonics, because we want a single NV center to have the spatial resolution. But this means we have to live with a very low signal. And to enhance this signal, to enhance the photon count rates, we will use photonic nanostructures. No? And this then in turn enhances your sensitivity. So far for the point of the magnetic sensing. No? This is why also for the magnetic sensing, you need photonics in the end. And the other point that I mentioned, your color center is a dipole. Well, every strong light emitter has to be an electric dipole at some point. And as such a dipole, your color centers can undergo a process called Förster resonance energy transfer, short FRET. Depends on who you ask. Some also say it stands for fluorescence resonance energy transfer. Yeah? Not going to argue about this. What we know is that this FRET process is highly distance dependent. If it's 2-point dipoles, it scales with 1/6 power of the distance. If you ask our colleagues from life science, they have demonstrated this, for example, for dye molecules with single molecule sensitivity, and they get nanometer resolution with that. So for example, they do have a protein, they attach to dye molecules, and when the protein is folding via this FRET, you can see the distance between these two dye molecules. This is how specific this can be. And also there, of course, you need an optical readout, because when these dipoles exchanging energy means it changes transition rates and then lifetimes change, no? And fluorescence changes. And this is why also here we need an optical readout. In essence, you need a donor dipole. You excite the donor dipole. Instead of radiating its energy, the donor dipole transfers its energy to an acceptor. In the results I'm showing you, the NV center plays the role of the donor, because often you want this donor to have the longer lifetime, to give it the time for this energy transfer before it ready. And before I go into details, I would like to show you two first applications that show you what we can do with this technology. And the one here on this side is a magnetic image. It's a quite new one from cooperation I have with the Johannes Gutenberg University in Mainz with a group of Matthias Kloy. And it's also a one that we have for the first time recorded with one of our commercial NV scanning microscope. What you see here is a material. In short, you can call it FGT. What's so special about this material? You can make ultra thin magnetic flakes by exfoliation. So it's something like graphene, just magnetic. And interestingly, it's not really known how this magnetic properties change with the thickness. So you can make flakes of different thickness, but in the end, you don't know if you have a multi-domain or a single domain. It's ferromagnetic, yeah, but you don't know this domain structure. And this is why we started this collaboration, because often when people are working with these materials, they make devices out of it. This goes especially into direction of spintronics. And then they are measuring with transport measurements, for example, and they integrate over the whole flake. Now you get something out, you make a device again, and you get something totally different out. And then you're asking yourself, why? And now we've come to the point that we have here a really tiny flake. I mean, you see here, the scale is just microns. And obviously, we see here we see a strong structure in the stray field of this flake. So that means it's a strongly multi-domain structure. And this is maybe to motivate for you why this NV magnetometry with the tip is interesting. So we can have, in principle, any magnetic sample. We can scan the NV over it. We can measure the stray field and then try to conclude back onto what's going on in the sample. And we can do this with a very good spatial resolution. So this is quite new results. This is why I choose it. I think that helps you to see that there's really a need for such measurements, especially also in material science. You might have realized that I draw the spin here at the tip with an angle towards the tip, yeah. And this is because really the NV center is oriented under an angle in the diamond. In our case, typically it's not exactly sticking out of the diamond or in plane. No? So this just as one illustrative example, right? This is really performed by measuring the Zeeman shift of this resonance. Yeah. And no, we are not doing this on purpose. It's just the typical orientation of the synthetic diamonds is 100 diamond. And then you have the NV centers because they are oriented along a 111 direction. They are oriented under an angle of 52 point something degree. Now, so it's not on purpose. Just sometimes you look at the stray field images and you think, this is not what I expected. But then you have to keep in mind that we are not measuring the field that the component that comes out of the plane of your sample, but you're measuring the projection under an angle. And then it's if the field comes out under a certain angle, and you're scanning over it, you always have to keep in mind that you're projecting under that angle. It sometimes makes things look asymmetric that you would expect to be symmetric. Exactly. Any more questions? So, and now, but this is rather the standard way to use the NV centers. And what we have then been looking into is also with this background of the life science, we know that this FRET is a very well-known process in the life science. So can we also do this with our color centers? And as the very first thing we did, well, this is really a quick and dirty experiment. We had some graphene flakes in solution. This is what you can buy from the graphene supermarket or something. And we put it on a diamond where we have the NV centers very close to the surface. In this case, it was 7 nanometer below the surface. We see, okay, at the points where you get a lot of graphene, the lifetime of the NV centers goes down. So we can see there's the points here where the lifetimes goes down. We also can see the Raman signal of the graphene. So this is where the graphene is. And you see, indeed, there is a strong coupling. We have two different systems. We have the NV in the diamond and something on top. And still we can see this strong FRET here. And this motivated us to go into that a bit deeper and to see if you have really the possibility to do the multifunctional sensing. Yes? Mm-hmm. Mm-hmm. When we would do this with the scanning tip, right, we would also end up with a resolution that is on the order of the distance of your NV to the sample. So this would be roughly the same like in the magnetic images. Of course, if you're really working in the same molecule, no? Then you get even better resolution. But in the end, also here, it will be limited by the question, how close can I get the NV to the sample? Yeah. This is more or less the limiting factor also here. I mean, here it was just to demonstrate, right? So here I cannot really give you a resolution in that sense. No. It also depends a bit, right? Because on the distance, this 1/r to the power of 6 is actually for 2 point dipoles. Sure, the NV is a point dipole, but here the graphene would be a 2D dipole, and that's also a bit different. It's not necessarily a 1/r to the power of 6. So this is just the simplest example. Depends a bit. Okay. So, and the question is, does this work in parallel, right? So can you still do the magnetic sensing when such a thread is running? I'll come back to that later. Now, and then I choose one example of this temperature sensing. And this is not my work. This is a work from Dirk Englund's group at MIT. They put nanodiamonds. You can see them here as little dots. Yeah, they put them onto a transistor. And then you can do something interesting. I told you if you have a magnetic field, the two resonances split, right? But now the question is, what happens when you're changing the temperature? And changing the temperature, of course, means changing your distances between the atoms in your crystal. So it's like straining the crystal a bit. And when you are changing the distance of the atoms around your color center, of course, you're changing the electronic wave functions at your color center. And what people find out is when you're changing the temperature, you're not splitting the resonances, but you're shifting the two resonances together with each other. And this, the group here has used to correlate two things, the magnetic field and the temperature. Because where you have current in the transistor, of course, it creates a magnetic field. Think of Biot-Savart's law, creates a magnetic field. And at the same time, you can see where the device warms up most. And this is what they have been showing here, that they can show shifts in temperature, and so independent of the shift in the magnetic field. This is an example of showing temperature, of measuring temperature with the NVs. I just picked this as an illustrative example, and I tell you that this nanoscale thermometry is something that at the moment for the life science, it's a really hot topic, because some guys 3 years back, yeah, I think 3 years back, measured the temperature within the mitochondria. Mitochondria are the power plants of the cell. The energy is being produced. And they found that the mitochondria in the cells are more than 50 degrees Celsius hot. And since then, this is an ongoing discussion in life science, because some people say this can't be the case. And other people say, well, we measured it. Yeah. And so there is also a need for this nanoscale thermometry. And I decided to put here some information on a future project. And this is a project I'm doing together with my new colleague in Kaiserslautern, Joachim Popesa, which somehow makes a bridge here, because before coming to Kaiserslautern last year, he was here at MPQ in the group of Ferenc Kraus. And there, it nicely links also to your talk, because they are also working with microfluidics. And what they are doing, they're using infrared laser pulses, have a microfluidic channel. They push cells through, And in essence, what they do, they're measuring the vibrations of the cells. They call this a molecular fingerprinting. With an ultra-fast laser, they're in principle, in real time, looking into the molecular vibrations of the cell. And this is really a powerful tool for life science. Just you need a lot of laser power. And if you shoot a lot of laser power in the infrared into such a microfluidic device with cells, it obviously heats up. The question is just how much does it heat up? So you're not sticking a thermometer into your 1 micron microfluidics channel, right? It's not working. So here we also need a non-contact thermometry. And at the moment we are trying also to use the NV centers here as thermometers, because they are even using windows of diamond for the microfluidics. So it could even be that we could nicely combine this here. Yeah? They're in principle using the diamond for the high transparency, but it could be a nice combination. So this is not just a thing that we can do magnetic imaging, or that we can use this dipole for the FRET, but we can also think about measuring temperature with the NV centers, and also with other color centers. Just in this case, I'm only mentioning the NV centers. Okay, now for the people in the audience that are a bit interested in the nanotechnology behind it, it's so easy to draw this tip with a spin on it. In reality, this is far from easy. First of all, because diamond, if you go to nanofabrication, it's not the standard material. Most people can do fabrication with silicon, but if you tell them you want diamond, they get like a bit afraid of their machines and whatever, and it's also not so easy. I already mentioned it, we have to do a lot of photonics. Why do we have to do this? Very simple physics behind it. Diamond has a high refractive index. So if you do not structure the diamond, only a few % of the light of your color center get to your detector. The rest gets totally internally reflected and is lost. This is the one thing. The second thing is we love the NV center for its spin properties, but we hate it for its emission properties because it has a very, very broad emission due to phonon sidebands. So always when we think about doing photonics, we need something that works broadband. Even if we could do nice high finesse cavities, it's not necessarily what we want here. We more want waveguides that can work with this broad spectrum. And still, we have to keep in mind, it should not only be a photonic structure, it should also be a tip that we can scan. And the two approaches that we have here, we can either make something that looks like a pyramid. This is done in so-called bottom-up approach. So this pyramid directly forms when the diamond is grown. And we can do a top-down where first the diamond is grown, color centers are created, and then it's processed into a pillar-like structure. And to give you examples, this is a joint work with a group of Patrick Maletinsky in Basel and Fraunhofer IRF in Freiburg. There we used such pillars, so cylindrical structures, and then we put them into the growth machine again, and we can make very nice regular pyramids with that. So depending on how you approach this, you get out a different structure, but still it's very hard for us to make the color centers at the tip of this pyramid, because when they are made during the growth, they will be everywhere in this growing diamond. So at the moment, as far as I know, all the results that you see are still obtained not with this bottom up, but with a top down approach. And then in the end, what you want to do is you need a diamond pillar, more or less cylindrical structure. And this you need to attach to your AFM head for the scanning. And this is typically done by having it looks like a cantilever. It's not really used as a cantilever, but yeah, a diamond beam with a pillar on it. And I'm not going to bore you with the details, but it's a lot of work. It's a lot of subsequent steps you need to make such a device, because you have to start with a comparably thick diamond plate, and you have to thin it by etching. And then you make 2 lithography steps to make this cantilever-like structures and to make the nanopillar. Of course, you have to align these 2 steps, these fabrication steps to each other, because otherwise your pillar ends next to the platform, which will not be helpful. And then you attach this to your AFM head. In our case, this is a tuning fork, this green thing here in this picture. And especially these 2 steps are tricky. We have mastered them partly in Saarbrücken. Now we also are working on it in Kaiserslautern. And here you can see some of our devices. Here you see this platform, still without the pillars on. And here you can see the platforms with the pillar. And here you see it's the beam has a junction, yeah, where it gets thinner. And at this point, you can detach your device and transfer it to an AFM head. And this is how this looks like. The picture you saw on the title slide. And this is now work from our own lab. If you say, okay, I cannot do this, I don't have the clean room or whatever, but I still want to work with the scanning NBs. Nowadays, there's good news for you. These tips are commercially available by 2 startups from Switzerland. But I warn you, be a bit careful about it. One of them costs 2,500 euros. So it's not like the type of AFM tip consumables you have when you're working with normal AFM, where your tip costs €1 or so. So it is commercially available, but there is still a lot of technology behind it, right? And depending where you want to apply this, you would need this to be cheaper and more accessible. And because of this, we are still researching into the direction, how can we upscale this process? And this is the dirty little detail that the people normally never mention in a talk, right? At the moment, we are working with tiny diamond samples, some millimeters. And probably each student working in my group has been crawling on the floor once, searching for one of them. There's some people with experience on that, it looks like, yeah. So the silicon guys, there's everything fine. You're working 4-inch wafers, you get a lot of devices out in one run, but we are somehow here limited still by the material. So can we do something against this? And the answer is yes, we can now. And there we are. We have been working together with the guys in Augsburg. I first wanted to say something on the photonics. Now that I forgot, I'm sorry, because what you might have realized, and I skipped this when showing the picture, our pillars are not perfectly cylindrical. This comes from the fabrication, and we have been doing a lot of simulations. And it still works. You don't need the perfect cylindrical pillar. This is the one take-home message. Also, maybe to give you a number, the pillars we are making are enhancing the count rate of a single NV center by a factor of 5 compared to the bulk. The new commercial ones, there are even some that are going to factor of 10 now, to an order of magnitude. So it's very good. And you also efficiently focus your excitation laser. So you need a lot less, laser power. And this is also good because the more laser power, the more background also you get. Okay, and then before I come to the material aspects, I also wanted to say that this is not the only point you can optimize, the photonics, but you can also optimize how you manipulate the NV spin. When you do this manipulation, for example, for the T1 measurement, right, there's 2 part we always have. One is polarizing the spin, the other is doing the microwave pulses. And here we have, in collaboration with the Forschungszentrum Jülich, we have been working with an algorithm they have. They call it red crab. It's a closed loop optimization. So you have a problem you want to optimize, and you give it an initial guess, and then you check how it performs, and you feed the new pulses back into your software, and then it optimizes it further. So you feed it back with what comes from the experiment. You see if it works better or not. And for example, we have been working on the topic, when you send your initialization pulse, is it better to have a short, intense laser pulse or a bit longer, not so intense pulse? It's about ionization and also again and such things. And there we have been then really optimizing the contrast a bit. So it's not just about the NV, it's also about how you do it. Here's the picture. You see where we have did this optimized readout that we can enhance the contrast. And the other point is what you do with this microwave. So normally you say, okay, I need to get from state 0 to state 1. You can just do a pi pulse, just on your Bloch sphere like this. But now imagine you're scanning your tip, for example, and the microwave field does not everywhere have the same strength. And now your pi pulse is not fitting anymore. So your spin manipulation will not be perfect. You lose sensitivity. And here we have been working on pulses that optimize this. So this is just a rectangular pulse. And then you go for the optimized pulse, and you see that with this optimized pulse, it's like you're going additional loops on the Bloch sphere to compensate for such variations. And you see that you get much better plateaus. You get better readout contrast. And you also get, what you can also do is that you get a more robust pulse. So your Rabi frequency, which means your microwave field can change more before the spin manipulation gets bad. So this you can also still do to optimize your NV center. This, as I said, was cooperation with the colleagues of Tommaso Calaco's group at Jülich. Okay, now you have done all this, right? It's still not going to solve that material science issues. You still have the tiny diamonds, you still have the few devices that you get in one run. To make this nanofabrication more efficient, we would need something like wafer scale diamond, right? And indeed, there is something like wafer scale diamond now. This is a work from 2018 from the group of Matthias Schreck. And you see here what they have photographed here is the first 4-inch diamond wafer. And I have to push this, it's single crystal. Of course, people can make polycrystalline diamond wafers, just the polycrystalline wafers. They don't have the quality you need for the sensing. And in this material there, we had a few years ago, for the first time, seen single NV centers. And why is this diamond so huge, or why is it so hard to make such a huge diamond? Well, normally if you grow diamond, you need a diamond for a substrate. So when you make this artificial diamond, you need some other diamond as a substrate. But because this other diamond is tiny, your diamond cannot be large. And what they have done here is so-called heteroepitaxy. So they're growing diamond on a non-diamond substrate. This is how they can crank it up. But we've seen in 2019, we have single NVs, but the spin coherence is bad. We ended up with a few microseconds T2. This is not very good. And only this year mainly, we received samples from a collaboration partner in Paris, from the group of Jocelyn Aha and Alexandre Thaler at the LSPM. And they do more or less the same. They have they are using so-called, they have some kind of a sandwich layer. So they're growing this diamond on iridium. The iridium has almost the same lattice constants than the diamond. They do this diamond growth. They call it heteroepitaxy. And now we know that this heteroepitaxial material is not as good as the one that's been grown on a diamond. But to make this better, they use this heteroepitaxial material, they drill holes in it with a laser cutter, and then they grow again. And when the diamond is growing into these holes, it's like it's not attached anymore to that bad diamond, and it can release some stress, for example, during the growth. And this is how the sample really looks like. This is the holes, no? And on top, you have this newly grown diamond. Please don't get scared. The sample is not broken. These strange lines are growth steps that can happen during the growth of the diamond. I have been told, yeah. I first also thought it was broken, but it isn't. And now we have looked into the samples again. We also see single NV centers, so it's a highly pure material. And we have been looking into this zero field splitting. So the position where we see the ODMR without any additional fields. And we see that when you are in these holes, you are closer to the ideal position than outside the hole. So it's really why this growth in free air, so to speak, you allow the dislocation density to reduce and the stress goes down. And there we are still looking into this at the moment. Just as a punchline, we are now almost reaching the T2 times of the electronic grade, so the best material we can get, also with this heteroepitaxial material. So it might really be the route towards larger scale diamonds and to making many, many more devices in one run, or to make larger sensing areas if you are thinking in another direction. Yeah. Yeah. We didn't see any because they are doing this so in principle, this material is electronic grade almost. You don't see any silicon in it. Mm-hmm. Yeah, I know the Audiatech was full of sample, but this one from LSPM, they have a high purity reactor. It's a general problem as far as I know if you have the wrong type of reactor. No, typically not, but you have to keep in mind also here, right, the final growth here is done when the silicon substrate is already removed. So here in this material, in this bad material, we might still have some silicon, but the layer on top, the high purity, we don't see any silicon anymore. Exactly. So this is a bit the material side. You need to, I was always suspecting that in this Audiatech, the silicon is even pulling down our NV coherence, yeah. But I'm not sure. We couldn't prove it, yeah. But this maybe as the material side outlook. So the manuscript should be on the archive soon. We have more data now, and we are analyzing this in detail. Okay, and now let's come back to this, what I mentioned in the beginning with this dipole and how you can do novel sensing with that. And for this, I want to show you results. We're also still working on this. Let me show you the basic experiment. So in this case, we had a 2D material, not the graphene, but a luminescent 2D material. In this case, it's tungsten diselenide. We also have molybdenum disulfide now. In a nutshell, you can grow this material really as a single atomic layer, and they are fluorescent. They have a excitonic luminescence. And in this case, it was the group of Igor Aharonovich in Sydney. They transferred this material, in this case, the tungsten diselenide, to one of our diamonds. And again, the NV centers are about 7 nanometer deep. And we have this overlap of the bands you need to see a thread. And now we were interested if we can really see a thread, because except for our quick and dirty experiment with the graphene, no one had seen this before, no? That the NV centers in the single crystal are making a thread. And then we had our flakes here. You can see this triangular shape, roughly, of these flakes. A lot of them lose this triangular shape when they're being transferred to the diamond. Not such a smooth technique, let's say it like this. But when we look here, you see everything that's here in yellow or green. That's the stronger fluorescence of this 2D material. And what's blue here is the weaker fluorescence of our NV centers. And if you then look into the lifetime of the NV centers, in principle, you see exactly the same picture again. And you see, indeed, under these flakes, the lifetime is going down. And you see here, obviously, they're not perfectly flat on the substrate because there's a lot of structure still, but this is from the transfer process. And we could even estimate the so-called thread radius, which in principle gives you the distance where you have 50% of energy transfer. So this was the first time we saw this. And now we ask ourselves this question I mentioned in the beginning. When we are going to that NV centers that are undergoing this thread, do they still function as a magnetic sensor? The question, I mean, you're strongly changing the transition rates here, obviously. No? And indeed, we were able to show also if we go to this NV centers here with this strong change in lifetime, we still see the ODMR, we see the reaction to the magnetic field. So indeed, the two processes can be running in parallel. So you can use the NV center as a sensor for dipoles in the vicinity and also for the magnetic field at the same time, the same NV center. Okay. And this now was our proof of principle, and we try to extend this. So first we are working on extending it to other materials. Now it's the molybdenum diselenide. We also have molybdenum disulfide now. This is in cooperation with the University of Jena. And at the moment, we are looking, for example, into the coherence time here of the NV centers. And this is challenging again. We are trying to make pillars with the 2D material on it. Always, if it comes to nanotechnology, it gets more complicated, I have the feeling. So, and this is, with this, we would like to try to transfer this near field sensing also to the application. Yeah, now that we know that even the NV centers in the single crystal can do the thread, this would be the idea. Then as a final remark, I would like to say that I think this is now a bit of still a growing topic. Yeah, there are a lot of companies now offering commercial solutions or pushing into that direction. And I really hope that this will be used in a lot of different fields in the future, and not only for the magnetic sensing, but I think it also has a lot of potential for these other applications and to show that the color centers are truly multifunctional sensors. Huh? So I hope I could show you that these nanoscale quantum sensors, maybe I should say atomically small nanoscale quantum sensors. This is an important point. You can do a lot about the technology to get nanoscale resolution, photonics, how you optimize nanofabrication. And I wanted to highlight this thread process and this dipole nature of the color center as a potential new sensing resource. Thank you for your attention.
Thank you, Elke, for a very interesting talk. Do we have more questions from the audience?
Yeah, so that you are also online, right?
So when you do the magnetic sensing, you're doing, of course, you have a single NV at the tip. when you were showing this near field, at least all of the results seem to be on an NV layer. So how do you do the local addressing then?
So in this case, we really did it as a proof of principle. So it's an ensemble of NVs, but it's not so many NVs in this case. We estimate we have about 10 NV centers in the focus.
Okay.
And then we really, in this case, we did the addressing by scanning our laser over the sample.
Okay.
So there it's just you bring it close by bringing it on the surface and then you scan the sample in this case.
In this case, then you can't use the microwaves, of course, because they don't do local addressing. I mean,
no, the microwave in this case doesn't do local addressing. Yeah, this addresses.
The two in the pillar.
Yeah.
Okay, understood. Thank you.
I mean, we have the microwave here, yeah, but of course it addresses the NV centers in the whole region. Yeah, exactly.
So what's about using microwaves in the near field regime? Basically, just as a continuation of this question, that should work in principle, or should it not?
Yeah, it could work. So our microwave antenna is not really a near field antenna. It's one of these omegas. So we rather thought in the other direction. We wanted to have in this omega, which is 100 something micron, we wanted a homogeneous field, right? So it's not, in this case, it's not really near field. So the microwave, as mentioned, in our case, it's not selective. If we want something selective, we need single NV or the laser addressing it, but the microwave is mainly everywhere. But yes, it could be a point to go into that, yeah.
I actually also have a question, if I may. So you talk a lot about FRET. So it should be a resonance energy transfer, right? So the two systems should be directly in the resonance. And then you mentioned also that you also applied magnetic field to check if your NV center is also magnetically responsive. When you do so, do you lose this FRET effect?
No, actually we don't, because in this case you have to keep in mind we're in a solid at room temperature. So all the resonances are very broad. So these optical resonances, they are not reacting to the magnetic field. So there I would say it's more or less decoupled. You have the optical response and the magnetic response, and they are not really coupling. You can use them both independently, so to speak. You're not shifting anything out of resonance. Yes, the spin resonance shifts, but the optical resonance still stays where it is.
So you mentioned that you use these layers of NV centers 7 nanometer deep. So first of all, how do you determine this depth?
This is really the calculated from the implantation energy of 6 kilo electron volts, right? So it's 7 nanometer plus minus, huh?
Yeah, of course, yeah, I know, that's why I was asking. And second, have you tried to go even shallower with the NV, or did you find this is the optimum for the FRET measurements?
I must admit, we did not try shallower yet. Yeah, because this was for, I must admit, it was for a technical reason, because the for the implanter, this was at this case the minimum energy we had. So we went to the 6 kV.
I see. Thank you.
Good. We don't have at the moment any questions in Zoom. That's the last chance, I guess, for the Zoom audience as well, to the people in presence. If not, Elke, thank you very much for coming and for giving a great talk. If anyone still wants to chat and catch up with Elke, she is still here until tomorrow afternoon, so maybe you get a chance. Contact please MCQST office if you're interested.
Okay.
And
thank you for your questions.